Very exciting. Welcome back. Although the groundhog was wrong, I want to put this on the record. This is absolutely not spring weather, and I object. There was snow on my car this morning. This is really not okay.
Thanks, Peter.
Didn't we say the groundhog was more often wrong than right?
Yes, sadly.
Just take the other.
That's what I said too. Okay, I have posted finally the FC homework. Hopefully you've seen this. Anybody started looking? I'm curious. I'm very curious. I'm very excited about this. I finally figured out how to get some origin data from that API. So that's potentially interesting. And I have some gender data in there. And I have lots of ideas for other things you could add. And I can't wait to see what you come up with. Super curious. So yeah, please keep me posted. I'm very curious to hear about the ideas you're exploring. The other thing, I posted 3 new readings for Thursday. So I haven't looked recently. If you haven't presented yet, then this is a great opportunity to present something. If you've presented already, but find one of them interesting, by all means, that's totally fine. But please sign up. Okay, so today I would like to talk more about this regression business that we started talking about already previously. I promised you that once you figure out some of these basics, this will be a superpower that you could take with you to all science ever, so long as you do anything empirical. This will come in handy. Okay. If you need to brush up, these are good resources. I'm going to cover some of this in class, but as always, never enough. So please go and read the original textbooks if you feel like you need more refresher. Okay, so let's start with a small case study and figure out how to get this out of the way. Okay, let's say you're trying to figure out, you're some marketing exec and you're trying to figure out how to best spend your advertising money. So this is data from 200 cities where you've spent money on advertising. You've spent money for TV ads, radio ads, and newspaper ads. And I'm breaking down all of the data here on sales in terms of these 3 dimensions that you've spent money on. Okay. So what's the first thing that strikes you when you're looking at this data? Sales as a function of advertising in these different media. All right.
The newspaper data looks a little scattered, or like I wouldn't trust that line as much as I would trust the TV one, maybe.
Mm-hmm.
Probably the TV is more effective.
And right, so it seems like there is some relationship, there's some correlation. It seems like you sell more, whatever it is you're selling, when you spend more on advertising, right? That's sort of an overall interpretation of this. And maybe the relationship is clearer for TV and radio than it is for newspapers. Is that fair? Okay.
Yeah, I was just gonna say that the budget is positively correlated with the sales, which you sound like you basically just said.
Right. Okay. Yeah. Sound good? Okay. So let's say you have some such data, and here are the kinds of questions you might want to ask. Is there a relationship between advertising budget and sales? Question mark. Or how strong is that relationship? Or which media contribute to sales? Or maybe which contribute the most? How accurately can we estimate the effect of each medium on sales? How accurately can we predict future sales? Certainly if you're doing forecasting and deciding where to spend more in the future, this is a kind of question you might want to ask. What's the nature of the relationship? Is it linear? To what extent does a linear relationship capture it accurately? Is there synergy among the advertising media? Is it sort of beneficial to combine maybe different media in terms of advertising? Okay, so just a number of questions you might want to ask. And this idea of regression we've seen already is very obvious way of trying to answer some of these. Very annoying. Okay, so we talked about this already some. For example, a linear relationship could look something like this. Y as a function of x. You have these two coefficients that you're estimating. So you observe values of x and you observe values of y. You know, x could be something like advertising expenditure. Y could be sales. You observe all of this in, say, 200 cities, and you're estimating these coefficients that describe this linear relationship from the data. Okay, there's obviously many possible linear models that you could build from all of these points. And the best model is maybe the one that minimizes this error from all of the from the predicted values to all of the observed values. What's left over is called residuals. That's the technical term. That's the difference between the actual observed values and the predicted values of the outcome variable of the y, okay, whatever's left over. And what strikes you when you're looking at this plot? This is a very relevant point. I'm going to come back to this. What pattern do you see here? Someone else. Kaya is too awake today. Yes.
Like looks like it's homogeneous, distributed above 0 and below 0.
Right, yes, that makes sense. So it looks like it's both above and below 0, which makes sense. So some points are overestimate, some points are underestimate. That makes sense. That was good. Yep.
Looks like there's like no correlation or these are residuals.
Yes.
Sorry.
This is what's left over.
I see. Well, I guess I could say
The error. That's the error.
There's no clustering at all.
Okay. So this looks random. It looks like a random cloud of points. It is kind of balanced above and below 0, but the part that it looks random is really important here. Okay.
So if it didn't look random, we should expect that some of the residuals were explaining the variability.
Excellent question. Let's pause for a second. What does it mean if it looks random or if it doesn't look random? Any thoughts?
I don't know, is not just to the relationship between the second.
One more time.
That our model is not correct. That's not.
Yes, that's the idea. Okay. If it looks random, that's a good thing. It means your model is a good representation of the data you're modeling, right? So our model is very simple here. It's a linear model. We had it on the slide before. And it is arguably a good representation of this data that we've observed empirically. If it does not look random, that means essentially that the model is maybe not a good representation of the data we're trying to model in the first place. Okay. And depending on the pattern and the residuals, we can learn something about what may have been a better model. And I'm going to show you more examples in a few minutes. But the key idea is, if it doesn't look random, if there's some pattern to the residuals, that's indication that your model, as specified, is insufficient to capture the data as observed.
Is that because you could be taking advantage of that pattern? Is that
right? That's right.
Okay.
Right. You could be, modeling the pattern more explicitly and precisely. Okay, very good. All right. So, least squares regression is the standard kind, the traditional kind. You will have learned about this in some stats class at some point in college if you've ever taken one. And so you find this least squares regression line by minimizing the sum of squared errors. Errors are, the difference between observed and predicted. We're trying to minimize that. Okay. So now how do we know how well your model fits? Let's say you have some true relationship in your data here, represented by this red line. let's say the actual true relationship in the data is y is 2 plus 3x. Maybe that's the real relationship. And obviously there's some noise and measurement error and whatever else. You can't quite observe it, purely ever. So you're seeing something that's somewhat distorted, and maybe you're estimating, the blue regression line over there based on the actual observed data. Okay, so the one you're estimating based on observations is the blue one. The real genuine one is the red one. You don't actually know the real genuine one unless you've artificially created the data in the first place, but that's never interesting, right? You're trying to get as close as possible to what might be the true relationship. You don't know what the true relationship is. Obviously, you have these estimates. Imagine then you're doing this over and over again. Okay? Let's say you take a different sample from the same population, and then you're estimating this least squares regression line again from that new sample, and you keep doing this over and over again, right? The idea is that the average of these many least squares regression lines should be pretty close to the true population regression line, right? So this is analogous to what you will have maybe learned about in stats 101 or something, about estimating population means of some random variable. So there you talk about how accurate this mean of the sample is as an estimate of the true mean of the whole population, and you talk about these standard errors. And standard errors can be used to compute confidence intervals. For example, 95% confidence interval is the range of values such that with 95% probability, the range will contain the true unknown value of this population mean, the one that you're trying to estimate in the first place. Right? So 95% of the time, you have the true value of the mean in your range there. Right? So it sort of gives you a good sense of how far off you are from the true population mean. Okay, so this was estimating means of populations from samples. In much the same way, you can talk about these standard errors and confidence intervals on these regression coefficients. And so, for example, 95% confidence interval for some regression coefficient beta takes approximately this form. It's the estimated coefficient, the one you get in your regression summary in R, plus or minus 2 standard errors for that coefficient. Do I have an example here? Let me see if I can show you one to remind you. We talked about this. Where did we talk about this? Let's see, do I have one? Yeah, okay. So here is, I'm going to come back to what all of these are. It's not important for now. But just as an example, we saw these before. You have some coefficient estimates. That's the estimated beta. And you have some standard errors. Okay. So the way you interpret this is to say that the true relationship between whatever this variable is and the outcome is this value plus or minus that, plus or minus 2 that, I guess, 2 dash that, times years of education. Okay. So in other words, you want your standard errors to be as low as possible so that your coefficient estimate is as true as possible. And that would also show up in the statistical significance and the p-values that we talked about that last time. Okay. So you'll see that when you have huge standard errors, your coefficients will be relatively insignificant because you can't quite pinpoint the true value of those coefficients. And you'll see that when you have high standard errors, the coefficients will be highly statistically significant. Okay. Okay, so back to
Why should it not read?
yeah. this has to do with how these standard errors are defined. I don't remember the arithmetic, the math exactly for Y2, but it's sort of some obvious derivation of why that is the case. To get to 95% confidence, you need that 2 there somehow. I don't remember exactly. Hence the book.
Standard error, standard deviation?
No, standard error in the same sense as standard error on these sample means. So the plus or minus value, how far off you are from the true
I see. So it would be
mean.
like a standard deviation of the mean.
Yes,
Okay, gotcha.
yes, that makes sense.
And that's how it gets to 95%.
That makes sense.
2 standard deviations.
Yes, correct. Yeah, that sounds right. Okay, very good. So, okay, so now how do you, let's say you have estimated some coefficients. We're talking about the same sales data and as a function of advertising, and you have something like this from your regression. So you'll say that in the absence of any advertising, that's the coefficient, that's the intercept, the beta 0 coefficient. Then sales will on average, I don't know where the fall comes from. I suppose the estimated beta would be negative here. I don't actually have the values. Wait, no, that doesn't make sense. Why would it be fall? Oh, fall between, never mind, not fall. Not fall as in drop, but fall between these values. Right. Okay. Similarly, for every unit increase in advertising, that would be this thing here, the expected sales will go up by this amount. Okay, that's the slope of that regression line, plus or minus the standard errors. Okay, so we talked about how this is great for empirical research, because essentially this allows us to test the null hypothesis that there is no relationship between these two variables, and decide to accept the alternative hypothesis that there is some relationship, there's some correlation between these variables. And that is very useful when we are trying to think about maybe causal relationships. We can't get quite there with just regression, as we talked about, but certainly correlation is one of the ingredients we need for a causal relationship. So it's useful to be able to measure the strength of this correlation. Okay. Here's another example. Let's remember this. So I have a few points there, and I have the estimated linear regression line drawn in blue. And this is the actual R output for that. So you see that when x equals 0, the predicted y is about 3. Okay, that doesn't quite match what you're seeing here, because somehow this is drawn to be higher, but the intercept there is 3. Okay, and you see that for every unit increase in x, y goes up by half. Okay, so those are the estimated coefficients there. Yes, nothing surprising, hopefully, here. Right, two coefficients, sorry, one coefficient and the intercept, two coefficients get estimated from these observed orange points. Those are their values. They're both statistically significantly different from 0, so there is some relationship of this form that can be learned from the data. Okay, right, remember this one. Okay, so now let's say we want to make let's say we want to make this slightly more realistic. Can we extend our analysis to accommodate all predictors. Sure, I mean, we could build one, we can estimate one regression for each of the predictors. That's one way of doing this, right? So I can run 3 separate regressions and estimate all of these, and I get these coefficient estimates. So I can see that they are all statistically significant. So, you know, all of these regression lines make sense. Okay, and I can see what their values are. So TV sales gives me, TV advertising gives me 0.04 more sales for every unit. Radio advertising gives me 0.2. And what is this? Newspaper advertising 0.05. And so I could conclude from this which one is most effective. Radio, because it has the highest return. Okay, and then TV and newspaper are about the same. If anything, newspaper seems more worthwhile, maybe. Okay, so this would be the interpretation of this analysis. Okay, so remember this too. What if instead of doing this separately, we put them all together in a regression? Okay. So now we give each one of them a separate slope coefficient, have one joint model for all of them. Okay. We talked about how this is a really powerful idea when we're doing whatever hypothesis testing of any kind, because essentially the interpretation allows you to assume that the other things are held constant, which is very useful in terms of, you know, removing plausible alternative explanations here, right? So I could reason about how radio ads impact sales while holding constant TV and newspaper ads, which is a much more powerful conclusion to draw than to do this independently. Okay, so here's what happens if you do that. You see the estimated model on the top right over there. What stands out? And I've copied the 3 that we had, the pairwise one, I've copied that on the left. What stands out to you? Yeah. No effect of newspaper, because I can't really conclude that this coefficient is different from 0. Yes, the estimate is negative, but I don't have enough evidence to conclude that it's different from 0, even though it's a little negative. So I can't really say anything about it, except that it's indistinguishable from 0, which means that there is no correlation anymore between newspaper ads and sales when I control for TV and radio. Okay.
This is assuming that we are already spending money in TV and radio, right?
Yes. Yeah, there's some. Yeah.
But for example, if a company is only paying for newspaper, then we would use the single market because.
Right. So here maybe the setting is you spend money on these 3 different media, advertising money on these 3 different media, and maybe you've done it at the same time. You know, maybe ads ran over the course of some periods in all of these, and they were in parallel, right? You could have had the same ad or something, you know, different media at the same time, and you're trying to figure out kind of what's the impact maybe on sales, something like that. No, so that's one thing we observe, right? We lose newspaper when we're doing them jointly. What's something else you observe?
Radio is still the highest.
Radio is still the highest, but it's lower than before a little bit. Okay, can't read too much, you know, they're close enough here maybe, but still a little lower than before.
Constant.
the intercept usually doesn't matter, right? The intercept is how much sales can you expect when you're not spending anything on anything. It doesn't really, it's not a useful thing to interpret in general. And also maybe not here. I look mostly at the coefficients for the interesting variables, which are the three I'm testing hypotheses about. Yeah, you could reason about the intercept, it's just usually not very interesting. So I guess two important things to remember here. One is that the multivariate analysis is usually more powerful because it allows you to, reason about effects of one variable while controlling for the effects of others. Always a good thing. And two, that these may be inconsistent. You may reach different conclusions, when you're modeling stuff jointly compared to when you're modeling stuff separately. Okay. So prefer the multivariate approach is the advice. Okay. We saw interaction effects already. Okay, so we can extend the model with an interaction term, and that would allow us to reason about moderators. When we talked about this last time, so I'm not going to go over this again. Okay, right. Here's another example, I guess, of interactions. Let's see. Okay. Yeah, so very quickly, we've talked about this before. Here we are having credit card balance as a function of income. Okay. And we have students versus non-students. So if there is no interaction term, we're fitting two parallel lines to the data, one for students and one for non-students. They have the same slope, right, by construction. They may have different intercepts. In this case, turns out that students carry more credit card debt in this example for whatever reason. But the slope is the same. Alternatively, if we have an interaction effect or an interaction term, you also see the slope varying between the two. And we talked about this at length last time, so I'm not going to do all of this again. Okay. It's another example of the same thing. Okay, so now what are some of the things to be careful about and keep an eye on? Here's one example. Potential problem is that the observed data is non-linear, and your model here is only linear. Okay. So what do you expect will happen? Well, here's an interesting diagnostic plot that you get by default in any statistical software. You get this by default in R. This is a plot of the residuals versus the fitted values. The fitted values are the estimated Y's of that blue regression line. And the residuals are whatever's left over. We talked about this earlier. So the red line here is just some sort of interpolation, some smooth line through these points. The residuals are the black circles. If this were your residual plot, what would you conclude from this?
Use a non-linear regression.
But in any case, this does not look randomly distributed, right? There's a clear pattern in the residuals here, right? So this would tell you that your regression line, your regression model is insufficiently capturing the data as observed.
Sorry, like this picture is a little bit different from the previous residual plot because I remember the last residual plot, the x-axis is the x in the left plot, and here you're showing fitted value, which is y.
Yes. Let's see. Oops. I don't know if I could do this live. I could show you the same kind of residual plot that I showed you before, and it would look the same. It would show the same pattern. I don't know if I could do it live. I don't want to risk.
Just any
messing
insight,
something
like which one you would take.
So this you get by default as part of any. In R, you get this by default when you're estimating a regression. So this is a very standard thing to observe and inspect when you're estimating a regression. So this is very normal kind of plot to look at. But this would immediately, raise some alarm bells with you, right? It would tell you that you're probably missing something with your model as specified. Okay. So, you could try, and obviously because we actually see what the relationship is, we see that it's nonlinear. You could try to model a nonlinear relationship instead here. For comparison, this is the equivalent residuals plot for the other example we looked at earlier. Okay. So hopefully you see that this looks very much like the one we had as an example earlier. They look random and sort of a random cloud of points. There's no clear pattern in the residuals here, which tells you that the estimated regression line is valid. Yes? Okay. Now, what if I told you that when you try to estimate this regression line for this example data set, you get exactly the same coefficients up to the third decimal in both cases? Would that surprise you? Furthermore, you get exactly the same goodness of fit, which is a value that tells you how well the data fits the model. What would you say if I told you that this were the case?
Probably surprising. So you could, it's not hard to imagine that you could just take the right plot and move the dots horizontally.
So it's not surprising that I could construct an example like this. Yes, I agree. So you agree that it's possible for this to happen, but then usually all you have is, an estimated regression in R that you base your research conclusions on in your ICSI submission or Chi submission or whatever it may be. Okay. And by the way, it's not usually just a handful of points and two variables that you can easily, visualize and debug. It's usually a very complicated thing with, many thousands of data points and lots of variables and so on. So you can't actually do this kind of inspection in the same way that we can do here. Okay. So this looks bad, right? Because that means that, your same model explains very different phenomena. Seems unlikely. Okay. Here's another example. Let's see, what is this about? Okay. On the left-hand side, we're talking about linear regression of fuel consumption miles per gallon as a function of engine horsepower. So you can imagine that the more powerful the car, the more fuel it uses. And the bigger the engine, the more fuel it uses. And this is the residuals versus fitted plot for a linear regression of those variables. What do you see? Non-randomness, right? There's some clear pattern. Okay, and maybe you can see that as sort of non-linear in this case. So that would maybe, by inspecting this residuals versus fitted plot, would lead you to suspect that there is instead a non-linear relationship between horsepower and fuel consumption. Then you would go back and include a quadratic term, maybe in your regression, and then re-estimate the model with a quadratic term in there. And then you would plot the residuals versus fit it again and look at that. And be happy that it looks much more random in the second case after you've included a quadratic term. So now, this would tell you that your linear model is insufficiently complex to capture the relationship in the data as observed.
How do you choose the new relationship? It's mathematical for QB.
You can fit any polynomial ultimately to this. The idea is, what is the simplest model that you can fit that explains the data well enough, right? And you usually start with the absolute simplest. Most often it is linear models. Sometimes it's linear models on transformed variables. I'm going to come back to this more in a second. So most often, most everybody does linear models because they're very simple and very easy to interpret. And rarely do people model nonlinear relationships using quadratic terms, and almost never with something more complex.
Yeah, and even if you add them to the model, I guess if they're not related, the coefficient will be 0.
That's right. Yes. Okay, now back to our example from a minute ago. Remember the example? What was I right? I don't know where I was going with this. I guess to illustrate that you could have maybe modeled a quadratic relationship here. Okay, this was one type of issue. Here's another type of issue. Here I'm showing you 3 examples of time series data, and these are again artificially generated in such a way that in the topmost example, there is no correlation between adjacent points by construction. It's all sequence of random points. But the more you go down, the stronger the correlation becomes between adjacent data points by construction. This is just an example to illustrate this. Okay. So you can imagine that things like, I don't know, stock prices or price of Bitcoin, or whatever it may be, gas prices, whatever, they probably show some correlation between adjacent values, right? If Bitcoin is, how much is Bitcoin these days? Is it expensive again? Dollars per what? $60 per Bitcoin? $65,000. That's not cheap, I'm gonna say. Yeah. Right. So if it's $65,000 today, it's probably not going to be, $10 tomorrow, right? It will take some time before it becomes worthless again. Right. So the value tomorrow is probably going to be relatively close to the value today. Same for gas prices, same for lots of other things. So this is something that can happen naturally quite frequently. Okay. So that's fine. But that also means that your estimated standard errors will tend to underestimate the true standard errors. So if you, right. These are plots again of residuals versus fitted, or just residuals. Plots of residuals, just residuals. So you can see the correlation between adjacent data points. You could see that, these values are correlated, right? They're all kind of in the same range before it jumps, and then they stay in the same range and so on. So when this happens, your estimated standard errors in the regression will be messed up, will be underestimates of the true standard errors. What kind of error will this lead you to, will this cause, will it lead? We talked about how the markers all ran out. Markers here. Thank you, Owen. Oh, I didn't hit anybody. We talked about type 1 and 2 errors before. Which one are we at risk of making? Kaya,
think type 1,
explain.
if we're underestimating the error, and the error is higher in reality, then it's more likely that our model is wrong. And when we conclude that, like, our hypothesis is correct, but it's not, that's like type 1.
Yes, false positives, right? This will lead you to identify statistically significant correlations or coefficients that shouldn't have been there in reality. Okay. So, you know, an assumption of all of this kind of modeling is that the error terms are uncorrelated. If you're to trust to interpret the estimated coefficients in their standard errors. If that's not the case, if the assumption doesn't hold, then you know your model is arguably invalid, unsound. So you shouldn't really trust it, interpret it. Yeah.
So what do you do about that?
Use a different kind of model, where
That's tailored to time series?
that's right. Yeah. So we'll have examples of that in a week or so. Yeah.
I mean, how do you detect the correlation error?
By inspecting, in this case, the residual plots.
Like, to be honest, the second one and the third one doesn't look too much different to me. It looks pretty random, although it's not random, I know, but like still some great randomness in that. So how do you accurately tell that this definitely exists some kind of correlation?
Is there some way to do this without your eyes?
You're not gonna like it. You're not gonna like the answer. What's the answer? No. Come on, you know me well enough by now. What's the answer? That too, but no. You gotta have.
Very.
So you have a theory about the mechanism and the phenomenon, and you expect there to be correlation or not, and you to use that theoretical mechanistic understanding to guide your modeling.
Let's say, so I guess here your assumption probably be like your theory is that there's no correlation between time, and you got such residual plot, and how to use this evidence to show that your hypothesis, your theory is wrong.
So the goal is to disprove some hypothesis that this is time independent. So it suffices to show that there's a correlation with time or something like that. Proof, like existence proof. You're showing that it is time dependent. It is a function of time, but empirically observed.
I think. So it's not just from the residual plot. I mean, just one of the methods you can use to determine whether your theory holds or not, and you can probably do some other proof to say.
In this example, when I said theory, I meant, you know, you have a theory about what it is you're actually measuring and modeling. You know, if it's stock prices or Bitcoin pricing or something, gas prices, if I have a theory about what it is I'm modeling, I can theoretically expect that these things are not independent, that there should be time correlated. Because I know how the phenomenon works well enough to be able to expect that.
Yeah, that's easy to understand. But I'm just wondering if there's cases like you didn't expect this time relation, but you do the experiment and find, oh, wait, there exists some time relation.
Right.
How, in that case, I don't know how people can get to their conclusion.
Conclusion for what?
Like our hypothesis is wrong. This is actually time dependent.
Yeah. So you show empirically some correlation with time. You show that this is time dependent, that a model that models that correlation with time explicitly explains this well. You're showing that empirically. And that's evidence to question the original hypothesis that it was time independent, for example.
Okay, so basically you need to find some strong evidence.
Counter evidence.
Counter evidence.
Right.
Yeah. Okay. That's helpful. Thanks.
Yeah. Okay, so this is the reason why we talked about types of errors you might find yourself making when doing this kind of modeling. And these are some of the ways in which you might diagnose that. Here specifically, you would look at these plots of residuals and decide qualitatively if you need to do something else, if you can trust the model enough or not. Okay, here's another one. This is also interesting. So here, again, we're looking at residuals, and you're seeing a pattern, right? It gets more dispersed the higher the values are. Okay, so this does not look like the nice random cloud we were hoping to see. Okay. So the technical term for something like this is heteroskedasticity. Yeah, try saying that 3 times in, yeah, really fast. Heteroskedasticity. So that means that the variance of the error term increases with the value of the response. A way to fix this normally is to compress the range by, for example, log transforming those variables. Okay, so instead of modeling y as a function of x, this would result in something like on the left-hand side, you would model y as a function of the log of x, which you can always do. Okay, so if your observed variable is, I don't know, advertising expenditure in dollars or something, you transform that to advertising expenditure, the log of advertising expenditure in dollars. Right? And this becomes, you call this x prime, right? You call it something else. So then you have y as a function of this x prime, which is the transformed original variable. Jeffrey.
Can we use the absolute value of x or root of x instead of the log x?
Yeah. The absolute value of x would probably not help you here. This would happen when they're all positive, for example. So the absolute value may not help you. The roots could help you. Yes. The root could help you. The log can help you. You transform the data in a way that makes this problem go away. It's the fix here, but you have to do something like that. Okay, So, again, we've looked at these residuals versus fitted. So you can see we're getting a lot of use out of this one plot. Like we're, just one simple thing to inspect the residuals. Lots of use out of it, like all kinds of things we can diagnose and ways to fix them by just looking at one type of diagnostic. So not too bad in terms of money's worth. Okay. Long.
The last,
Sure.
I don't know how much this like makes it better though, because that doesn't still mean that like the data is the same, so like how is it like how is this better? I don't
So, okay, so first of all, I was wrong here, so sorry about this. The example on the slide is not this, but it's rather this.
Well, if you're a log transforming it, you're finding a different regression altogether, or just so
That's right.
measuring a different
Yes,
residual.
correct. So that is the answer. I want still. Thank you. I'll bring my own next time. The example I had there was log of y as a function of x. Right, so I wasn't logging the x, I was logging the y there. And you're absolutely right. You're estimating a completely different regression, right? So everything can change, which is why the problem may go away. Right? These become different variables. You're estimating something different. By the way, count variables, especially when it comes to like software related things, counts of lines of code and stuff like that, software metrics in general. Almost all of them are log normally distributed. Just I don't know why, right? It's just sort of an interesting natural phenomenon that the counts of people working on a project, or the counts of, I don't know, files they write, or commits they make, or lines of code they author, whatever it may be, counts in general in software tend to be log normally distributed. Super interesting.
It seems a little bit dangerous in a way to do this log stuff, because basically there's a relationship here, and it could be the error, or it might not be the error. It might actually be you didn't model it right. And I mean, I guess my question is basically, how do you know it's the error, not something else?
The error should look random.
Right, it should look random, but how do you know that it doesn't look random? Because the error increases. How do you know it's the error that increases with fitted values and not your model that's not capturing some linear change? Or okay, I guess not fitted values, but how do you know it's like the error that is increasing versus like your model should be changed?
I'm not entirely sure I follow. So the error is,
I think when you do this, the trick of it is that you are changing the model to better fit it. So what you're saying is exactly what's happening.
So I see. So if you change it, you get the log of y, then if all of a sudden it looks random, then you've done it correctly. If it doesn't look random, then that answers the question: is doing this trick won't work?
Yeah,
Okay.
you're changing your model. You're changing the actual model as well.
Okay. So you try it. You see it.
Yeah.
It explains it. Okay. Thank you.
okay.
If that's random, that's still not random, right? So we
The-
solve the problem, but the model is still not the right one.
But this is so much better than the other one. Yeah.
Okay. yeah.
Right, because it's not perfect, but it's so much of an improvement over the previous one. So at some point this becomes an art, and you call it good enough. Right, but I mean, this is much closer to something you would actually like to see than that. I think you will agree.
Yeah.
And you're right, it could still be not good enough, and you keep, doing other tricks until you're happy with how this looks.
So to make sure I understand the process, the point of this is you're identifying characteristics about your data. And if the current regression you're not using isn't random, you're changing the regression to better explain the relationship between the two variables.
Or the data, right? Yes. Yes. So I'm changing the regression by maybe adding a quadratic term or something if I have a nonlinear relationship, or I'm changing the data by maybe log transforming it to better satisfy these modeling expectations. Right. But either way, I'm doing something to make this more sound, more valid. Yeah. And so far, we've looked at these residuals in like a number of ways to diagnose a number of problems, and we've applied this one trick well, I guess two tricks. One is to add maybe nonlinear terms. The other was to transform data in some way. Right, so this you'll find at the end of this that there's just a handful of tricks that will almost always work well enough to get you out of trouble. In most cases, so it's actually quite satisfying. Just a handful of things that if you just consistently do systematically, you're in a good spot.
Well, the adding nonlinear terms thing was also a transformation, I thought, because you're just squaring it instead of like you're applying with the squaring transformation. Or am I misremembering?
So I guess you're right. So I'm calling that changing the model because I'm essentially changing the specification.
Yeah.
But yes, I'm doing that by hacking the data to include a fake variable that represents the squared value of the original. But I've changed the model specification. Maybe in this case, I haven't really changed the model specification. I've just replaced the outcome variable with its log, and I have the same model specification. Right? So. Okay, so here's another problem and trick. This is the one that I think most often gets you in the most trouble. So here we're talking about outliers and high leverage points. Let's consider the following two examples. We have some points with an outlier and the estimated regression line in blue as before. And we have some points with an outlier and the estimated regression line in blue as before. So first off, just as another distraction and for your amusement, would it surprise you? Would it surprise you if these are also exactly the same as the ones before? Okay, up to the third decimal. So that's arguably also bad, right? Because let's say you here four very different phenomena that, when modeled without too much care, would lead you to the same conclusion. Right, so let me go back to where we were. Okay, so here's what's happening. Both of these points, the one here and the one there, are outlier points because they don't fit the rest of the points well. And a way to determine this is to reason in the following way. How would the regression estimate change without that point? Okay, what would it look like on all the points except the one in question? And so in both cases, not true. In the first case here, you could hopefully see that if I take the outlier point out, the regression line wouldn't change all that much. It would change somewhat, right? These are collinear, but not too much. So whatever you're estimating with this outlier point in the data is not too different from what you'd be estimating without it in the data. Okay, so we call this an outlier point that is friendly, for lack of a better term. The one on the right is called a high leverage outlier point because it has high influence on the regression line. If I take this out of the data set, then the estimated regression line would be a vertical through these orange points here. Very different, right, relationship than the one you're modeling currently. Right, so we're saying that this has high leverage on the regression because without it, your conclusions would be absolutely completely different. Okay. So this bad, this less bad. Okay. So now, again, we're coming back to this art part of this. You need to make some artistic decisions in this kind of analysis, right? You need to, first of all, identify such points. And then you need to make some decisions about whether to keep them or whether to remove them or whatever else to do with them. Or maybe you go back to the original data collection or whatnot and figure out why they were there in the first place, and if there was a mistake or something in the way you collected your data or whatever it may be. But sort of it's a point of introspection and pause to figure out what had caused these in the first place and how you want to deal with them. Right? And obviously you can't remove all of your data, right? You can throw away half your data as outliers. Because it doesn't fit your predetermined conclusions or something, whatever it is you're trying to prove with your study, right? That doesn't work. Well, hopefully you will agree. But at the same time, you should do something, right, about points like these. At the very least, document, in your analysis that you have identified them and maybe decided to remove them or something. This is, I think, the most common strategy. People identify and remove a tiny fraction of their observations that would disproportionately, impact their regression estimates, and report conclusions on 99% of all of their observations, maybe throw away 1% or something. The 1% that would screw things up. So another thing here. So let's say I move this point from there to here. Okay. So the estimated regression line would be some horizontal going through all of these. And the coefficients estimated there would be highly statistically significant. That's the case. Because the error between these points and the horizontal line would be relatively small compared to, how far this is. Okay. So what I'm trying to say is, this is another one of those where you'd be making, well, I don't know if it's so much I guess it's a kind of type 1 error, where you would be concluding that some completely bogus relationship exists in the original data that shouldn't have been there in the first place. Right? And you could see how potentially everything changes from maybe no relationship at all once you remove those points. Right? Here's an example. Random cloud of points. Random cloud of points with a high leverage outlier. Okay, that's the data set. If I keep this in, I get this regression. Okay, so I'm very confident that that's, the linear relationship there. If I take this point out, I get nothing. Randomness. Okay, so anything can happen here. This is very dangerous, right? You can have anything from no relationship at all to something completely different. In this case, a perfect vertical, to anything in between. So very dangerous. Okay. I started this by saying this is probably the one that's most common and the one that gets me in the most trouble in practice. And hopefully you can see why it's very dangerous. Okay, so now back to diagnostics. There are some of these plots again that allow you to identify such points in a more principled way. There's something called residuals versus leverage, and there's some measures that tell you how much leverage do these different points have. And for example, there's these kinds of plots that would place certain observations outside of the harmless zone and into some high leverage zone. And that would allow you to pinpoint those, and you go inspect them and you decide what to do about them, whether to remove them or whatever it may be. This is the way to find them, and then you go and do something about them. Another way that's very common in practice is to not go through all of this trouble and to just say, I look at the distribution of observations for whatever variable, and maybe it looks something like this. So imagine some density plot like that. So maybe there's like 2 points that have extremely high values, and most of the points are here. Okay, and maybe there's nothing in between. If I look at a histogram of observations or something. So then I go and I look at these in particular, because I know those are likely going to have high leverage and may screw things up. I decided what to do about it.
So we do that for each chart.
Yes. Yeah, one at a time and always. Yeah.
What's the
It's the same one. Both graphs are this residuals versus leverage graphs that you get automatically, just like you get the residuals plots automatically. So normally there's some sort of funnel and shows you where the observations are within that funnel and what's outside according to this measure of distance. I don't know, this distance is some measure of leverage of distance.
where's that point?
Exactly. So here is just so far out that it's not even on it's off the charts, literally. Okay, it is off the charts.
So here we will not see it. So how we know that there's a point out that we should remove from that plot? It doesn't show.
Right. So you should be able to see these whatever ranges and whatnot, I think, in these charts. And here, the fact that you're not seeing these ranges at all would be an indication that something weird is happening. And then you go inspect the original data and you figure out kind of if something like this is going on. Yeah, so you should expect to see, something more clearly. If you don't, something weird is happening. Okay. We talked about this. All right, one more. This is also awesome. Talking about collinearity. Here is an example. I have two variables, calling them x1 and x2, that happen to be identical. Just because I created them. Okay. And I have outcome variable y that happens to be the sum of the two. Okay, y equals x1 plus x2 by construction. Okay. But can you guess what's going to happen? Well, yeah, they are the same because that's how we made them.
We can explain what does it.
That also y equals x1 plus x2. Is there any other way I can specify this model? Y equals 2x1, y equals 2x2, and infinitely many others. Okay, so I can't actually figure out what the right relationship is here in this case, because there's infinitely many ways in which all equally well fitting, right, in which I can describe it. That makes sense. So this is a problem, right? Right. So, right, when I'm trying to estimate this model, I cannot actually distinguish between all of these that are equally plausible. So, I probably get huge standard errors on the coefficients. Right, so chances are you will get some coefficients estimated because R, rarely complains, you get something back. But they will have high, large standard errors, because you cannot be confident that those are really the estimate, the real estimates. Let me show you. I actually have this prepared. Okay, so here is the same data I showed you and a model with both of them. Try this again. Okay. So it does tell me that 2 times x1 plus who knows what times x2. It cannot decide. Okay. And it actually, it tells you that it cannot do this. So in this case, you're sort of like, look, warning, essentially perfect fit, summary may be unreliable. It gives you warning signs that something funky is happening. So maybe this is not the perfect example because the values there were actually perfectly identical. Let's cheat a little bit. Let's make them ever so slightly different, still almost identical, but just ever so slightly different to trick R into actually doing something. So we have done that. And note that I'm getting, 2 statistically significant coefficients, and it's basically just weirdness. Yeah, this is close enough to the previous one, I guess. You're getting 2x1 plus basically 0 times x2, but you're still getting some coefficients here. That's estimated and thought to be significant. So then what do you do, right, when this happens? Obviously, you will agree that this doesn't make sense. And turns, you could get anything here, and these are unreliable, right? You cannot trust these estimates at all, right, when this happens. So what do you do? Ideas? Well, okay, but yes, but right. What do you say more? Say more about this.
I mean, just do not make them the same.
But except you don't usually make them; you just observe them, right?
Under correlation.
They could have just naturally occurred, right? So what do you do in that case?
By that balance.
In terms of modeling, not in terms of changing the data.
When the correlations.
Kaya.
Perhaps there is some way to make them the same variable or explained by the same phenomenon in your model. Like just say there's x1 and like average something like this.
Maybe, but
Well, there has to be some test for collinearity.
sure. I mean, you can at the very least compute the correlation pairwise between them.
So you can use that to detect it.
And how do you fix it?
You need to reduce the variable in that case.
What does that mean?
You need to get rid of one of the variables.
If they carry the same information by virtue of being highly correlated, that tells you that they measure the same underlying construct. In which case, it doesn't matter which one you keep, right? You have to throw away one. In this pair, in this example, you throw away one, you keep the other, because they measure the same thing. Because practically it doesn't matter which one you use if they're so highly correlated, right? Because whatever relationship one has with the outcome, the other one will also have the same relationship with the outcome. All right.
That makes sense, or like was kind of what I was going for, but like in reality, I feel like the numbers are more likely to be slightly different than exactly the same.
Yes.
So how do you choose which one to keep, or do you just try to choose on random, or would you try to average them?
Great. So if they're correlated, if they're too highly correlated, you have to drop all but one. We agree. If they're correlated enough to cause a problem with estimating the regression and having too high standard errors, you could choose to do something like we did for the survey instrument design. You remember a bit about factor analysis? So, you had this multi-item scale with lots of questions that were maybe all trying to capture the same underlying construct.
Yeah.
And we did some factor analysis to show that they all load onto some maybe, one underlying factor or something.
Mhm.
You could do something like that, right? You could do some dimensionality reduction to show that these all, essentially capture the same, or a lot of them capture the same thing, or maybe there's two underlying factors that explain, 10 variables or so. And you use those factors in the regression instead of the original, say, 10 variables. What one approach to deal with this? No.
Can you do this mechanically by solving for linear independence?
What's the goal?
Like linear algebra, when you're just when one thing is expressible as a linear combination of other things, that's you can just get rid of it. People, you can write a complete program to do that for you. I'm wondering if this falls over anywhere. Like this is like a straightforward case of that, right? I'm wondering if there are complex cases where you couldn't have R or something do that for you.
It will do that for you when they are straightforward like this, when there's no uncertainty.
Sure.
But in reality, there's enough noise that
You're right.
that you can do this.
There's enough subjectivity that you would have to decide which to draw.
Yes.
Okay. Yeah.
Yeah, because they're never this clean, as in this artificial example.
Yeah.
Right. Again.
I guess this might be a little similar to what Matt just asked, but how sensitive is the R warning? And like, would you always want to try to do the loading onto factors, or only if you notice that some things are freaking out?
Okay, so in practice, there's two kinds of things people do. You could do pairwise correlations between all the variables in your model, and you use some expert subjective interpretation of those values to decide what to do, and if there are things that are too highly correlated. There's also this variance inflation factor, which is another measure basically of that tells you which things in your model are highly collinear, and there's some magic thresholds for this in much the same way as there are magic thresholds for effect sizes, labeled as small, medium, large, and everything else. And you could use this kind of reasoning to say, these things are collinear, therefore maybe I drop all but one of them or something in this cluster. And because they capture most of the same information, so it doesn't really matter which one I keep.
That makes me happy.
In our example, since you're asking, do I have it? Yes, I do have it. So, right. So this variance inflation factor for our example here would tell you that the value of this variance inflation factor is 100 something, where the threshold is like 2. Okay, so that's like big red sign that something weird is happening. And again, the reason you're doing this is because you would, ideally want to have some trustworthy estimates of these relationships of these coefficients, right? Because you interpret those directly. That's the conclusion of your study. You're saying, how much does X vary? Or how much does Y vary when I vary X, right? And you want to be confident when you say, by 2, it varies by 2 units. Right? If you can't be confident in that estimate, the whole point is you're in trouble. Yeah.
So if we do the factor analysis before this, in theory, we will not have this problem.
Right. So you could do something like any dimensionality reduction here, like factor analysis would work. You could do that to reduce the collinear variables to, some small number of factors or something like that. You could do something like this. Usually, though, you have some regression with lots of variables, only some of which are collinear. Most commonly, if you have some that are highly correlated, you just drop all but one of them because they essentially capture the same information, and then you tweak your interpretation. When you describe the results of your analysis, you basically can interpret that coefficient in terms of all of the variables that were collinear, because they're all highly correlated, right? Maybe the number of developers working on a project is very highly correlated with the number of lines of code they write, like bigger teams write more code. So you can argue about effects in terms of either one of those if that's the case. You could do that. You could keep.
But should it be find a common factor of those variables to try to explain?
Right, or you
say
could
why we thought.
you could do something like this. Yes. So
In
either
this
one.
case, it will be not a moderator, a mediator. One of the variables will be a mediator.
Yeah, I see what you mean. In the factor analysis sense, you have some latent factor that causes your variables. I guess you could say that. Yeah.
Because I'm thinking, if I'm trying to build a theory and I have both variables, and then I just drop one of them, I need an explanation why I can drop one of them and still making conclusions about.
Well, the explanation is numerical, statistical. They're highly correlated. They capture the same information. So you measure the correlation between them, and you determine that it's very high, and you choose to drop one and keep the other arbitrarily, if you will. You could do this. Like numerically, nothing bad will happen. If you keep the first, drop the second, it will be the same as if you drop the first, keep the second.
Yes, but then I need to explain why.
Yes, then you explain why. But yes. You explain in terms of the correlation, and then you explain in terms of, again, some theory about why they're the same.
Right.
Yeah. Okay, a good place to stop. I would like you to please remember to sign up and present some papers next time. And also please bring a device with R, because I have some stuff that I would like you to do hands-on. We'll have fun in class together.